This video will discuss the calculation of a weighted moving average forecast and the determination of that forecast to minimize the mean absolute deviation. On the screen, we have 12 periods worth of historical data for actual demand for a product. The goal is to calculate a forecast for the demand for this product for the next 4 periods. Since the data is quarterly, we want to do the forecast on a quarterly basis for 4 periods. We'll use a 3-period weighted moving average. At first, the weights are selected arbitrarily. We'll have a weight of 4 on the most recent actual, a weight of 2 on the actual from 2 periods ago, and a weight of 1 on the actual from 3 periods ago. A manager could establish these weights if they thought that the most recent period was important for forecasting future demand. 2 periods ago was about half as important, and 3 periods ago was about half again as important. But they want to use 3 periods of actual demand as relevant for forecasting future demand. Because this is a 3-period weighted moving average, the first forecast will be calculated in the 4th period. A weighted moving average attaches the weight for each period to the actual that we've observed. So if we want to calculate the weighted moving average for period 4, we would multiply 4 times the most recent actual at that time, which was 720, 2 times the actual from 2 periods ago, which is 678, and 1 times the actual from 3 periods ago. We can do this very easily with a formula in Excel called sum product. We want to calculate the sum product of 3 actuals and the 3 weights. The 2 ranges are the same size, so it multiplies the corresponding values in each range with those in the other range. Because we don't ever want to change the weights as we move down the list of actuals, we'll use an absolute reference, which is a $sign. This just simply means that the weights will always be referenced from rows 2 to 4. In the denominator of the weighted moving average, we need to add the sum of the weights. This ensures that the forecast that we develop will be in the same terms as the original units of demand. With the formula developed like this, we can copy this all the way down to all the other periods in our forecast. So I'm just going to copy this down all the way to period 16. Now we have one problem that we need to correct. This formula works quite well up to period 13. As you can see, for period 13, we're calculating the weighted moving average forecast as a sum product of periods 10 through 12 and divided by the sum of the weights to get the final value. When we move down to period 14, we're referencing one blank cell. We don't have an actual for period 13, so what we would have to do to carry the forecast forward is simply substitute the forecast for period 13. I'll do this in the worksheet by just simply referencing the forecast and placing it in the actual column. The actual column is shaded gray for periods 13 to 16 to indicate that these aren't actual demand values. They're just simply replacements for the actual demand that are the current forecast. This has the effect of allowing us to calculate a forecast for periods 13 to 16. Weighted moving average is an averaging method. So eventually, as you see down in period 15 and 16, the forecast simply flattens out. It is, after all, an average. And we can see the flattening out of the forecast on the chart. Now we want to see how well this forecasting method performs. We want to calculate the forecast errors. The forecast errors are the actual values minus the forecast values. I start with period 4 because there are no forecasts for period 1, 2, and 3, so we can't calculate errors for those periods. Some errors are positive and some errors are negative. We miss the actual both on the high side and the low side. There are no errors calculated for periods 13 to 16 because the values in the actual column aren't actual demand values. They're just simply where we replaced the actual column with the forecast so that we could carry the forecast forward. We want to calculate an error measurement. We could calculate the average forecast error. The problem is that the negative and positive values for the error tend to cancel each other out, and we don't get a good indication of how good our forecasting method is. One way to solve this is to use the absolute value of the errors. So in the ABS error, or absolute error column, I'll use the Excel function ABS to calculate the absolute values. The absolute value simply removes the negative sign from the errors that were negative. To get an overall picture of how accurate the forecast is, we'll calculate the mean absolute deviation, MAD. In MAD, mean stands for the average, absolute stands for the absolute value, and deviation is just another term for error. So the name basically tells us how to calculate this error measurement. With the absolute errors calculated, we simply need to calculate the average of those absolute errors. The mean absolute deviation is 78.1, and it means that on average, our forecasting method, the 3-period weighted moving average with the weights of 4, 2, and 1, misses the actual by about 78 units for the historical periods where we have data. This gives us an idea of how accurate this forecast may be as we move into the future periods. One way that we can improve the forecast is by experimenting with different values for the weights. For instance, if we wanted to simply have all periods weighted equally, we could use any set of weights that was equal. It turns out that the MAD for that forecast is a little bit higher. So our original set of weights was better. Another way we can do this is to use Solver to minimize the mean absolute deviation by selecting the best weights. Solver is in the Data ribbon of Excel, over to the right. If you need to add in Solver, you would go to File, Options, Add-ins, and click on the Go button next to Manage Excel Add-ins. You would then check the Solver add-in, which is already checked on this machine. When we open Solver, we see that we need to set an objective. And the objective here is selected as F22 because that's where the MAD, the measurement of error, is calculated. This is a measurement of error, so we want to minimize it. The changing cells are the things that we can adjust in order to improve the forecast, and those are the weights. In this case, there are no constraints on the weights other than they can't be negative. And by checking the box that says Make Unconstrained Variables Non-Negative, we will avoid having negative weights. We want to use the GRG nonlinear solving method. If we click Solve, we'll see if the weights improve over the previous forecast. The thing to watch will be the MAD to see if we improve upon 78.1. So we did improve on 78.1. We now have an MAD of about 67.65, and we can see the weights that Solver selected above. It's an interesting set of weights. We're using 1 period ago and 3 periods ago to forecast, but 2 periods ago, the data is not as effective to forecast future periods.